Getting recording going. So now we're getting into Rank-Deficient. These squares. At least up to a certain point in these notes. We'll see how that goes. All right, so the problem is almost the same. Minimize norm of b minus ax. But so okay, so a is n by n, and now the rank of a is less than n. Okay. Now, so now that A actually has a null space, that means that the X that minimizes this 2 norm is no longer unique. Because you could add to X, if you have an X that does minimize B minus norm B minus AX, you can add any vector in A's null space to X, and that will still minimize. All right. So we want to have a unique solution. We need additional criteria for X to get uniqueness. Now, the most typical additional condition we can impose on X, as an example, we can find a solution that minimizes this norm, but also this norm. So the minimum norm solution. Okay. In some applications, you might want like a smooth solution. So maybe you minimize the norm of some matrix times X. Like for example, matrix could be something approximating the derivative, because if you have a vector X that represents a non-smooth function, and you take its derivative, it's going to be oscillating all over the place to be larger in magnitude. So if you require that the norm of some sort of discrete derivative of X is smaller, then that ensures a smooth solution. But we're not going to get into conditions like that, but we will talk about this condition, finding the minimum norm solution. Actually, this is a condition that MATLAB uses. So A \B in MATLAB finds X such that B minus AX, the norm, and the 2 norm X both are minimized. So whatever kind of A you have, whether it's square, vertical, non-vertical, rectangular, it's going to give you this. So for example, if A is squared invertible, that's going to be 0. And there is a unique solution, and so that would trivially be satisfied too. If A is rank deficient, then the solution is not unique, so it finds X that minimizes this and is as small as possible. If B is not in the range of A, then this can't be 0, but it'll make this as small as possible. Now, the methods that MATLAB's / uses depends on the problem. Like, for example, if in the squared invertible case, it's going to use Gaussian elimination with partial pivoting, most likely, especially if it's a dense matrix. Or if we're solving a least squares problem, I imagine actually, I don't know what it does. I'm guessing it would use QR factorization because that would be the smart play. But often if you look at not the help page for a MATLAB command, but the documentation page, you do like doc in the command name at the prompt to get it. It'll give you some indication of what algorithm it's using in its implementation and references. So that's been helpful sometimes, like for research and such. Okay. So what we're going to look at is how to modify the approach to solving least squares problems in a full ranked case to work with the rank deficient case. In particular, dealing with the QR factorization. So that we look at, it's called QR with column pivoting. And with Gaussian elimination, you need to interchange rows. So it's a similar idea that if we try the QR factorization algorithms that I've shown you on a rank deficient matrix, it's going to break down. So we need to form some kind of permutation to make it work. So, the condition that I described before. Okay, so if I write A as a column partition, and the same for Q. Q is m by n. This is like for a full QR factorization. Now, what the property we've been able to count on before is that the span of the first k columns of A is equal to the span of the first k columns of Q. And we saw from Gram-Schmidt that each column of Q is a linear combination of like QJ is a linear combination of A1, A2 up to HA. So this condition does not hold if A is rank deficient. The reason is these are orthonormal. Therefore, they're certainly linearly independent. So this span here is always a k-dimensional subspace. But if rank A is less than n, for some value k, we're going to have a set of linearly dependent vectors here. So this span could be a subspace of dimension less than k. So at some point, this equality is going to fail to hold in a rank deficient case. All right. So what we do is, instead of computing A equals QR, what we do is we get factorization of this form. So it's kind of like the analog of PA equals LU. If A capital pi is equal to QR. So pi here is a permutation matrix. And because we're multiplying A by pi on the right, it's going to interchange columns rather than rows like we had in Gauss elimination. So I'm gonna pick up one of the algorithms I've shown you from full rank case, a householder you are, and how it'll be adjusted for to handle a column type. So and we can adapt any P algorithms we've seen for this purpose, but so the first thing you do is rotation here. Okay. Looking at how I wrote this up here in my notes, it's like, this really could have been written better. What the hell was I doing? I mean, the idea is there, but yeah, probably could be explained a little better. Although there is an example in the notes.
You can make the risky decision of changing it on the fly.
That's pretty much what I'm gonna do, yeah. Okay, yeah, like I said, how that goes depends on how comfortable you feel with the concept. So this one is not the hardest. Okay, so first thing you do is so define A1 to be equal to A times a permutation matrix pi 1 and pi 1 swaps column 1 to column J, where J is chosen such that it's whichever column has the largest two norm. Right. So it's similar to partial pivoting. Instead of examining individual elements, you're taking the two norm of each column of A. Whichever column has the largest two norm, you put it in the first position. So once you do that, A1 is overwritten with a householder reflection applied to A1, like in ordinary QR factorization. So that H1 applied to the first column of A1, the superscript here indicates that's after the columns have been swapped. Is equal to a multiple of E1. Oh. I'm gonna have to check on. Because here specified that the diagonal entries of R are positive, but I remember from full rank QR, when using householder, you're transforming your column vector so that the first element is equal to some constant alpha times E1. And alpha will be plus or minus this. But here my notes, it says that it's going to be positive.
Didn't we say something about if we required that the diagonal entries be positive?
You-
It gave us
Uniqueness. It gives us uniqueness.
uniqueness.
Well, that's one way to get it. Yeah, or with one reason to stick with this. It's not the most numerically stable thing you could do, because forcing it to be positive could increase cancellation error in your householder reflection. The vector V that you define that makes a householder transformation work. I'll have to check on that. But for now, we're just gonna stick with this. So, okay. Now, since I'm working on a new edition of the book, these things I have to take into account. Okay. Actually, as I look in the example here. Oh. In the example, I have a R that does not have all positive diagonal entries. I guess because it's doing householder in the numerically safe way, where the remaining non-zero entry is allowed to be positive or negative. Okay. Man. Yeah, these notes and therefore my book are gonna need serious work here. Okay. Also, for one thing, yes, I say in the notes, like to maximize R11, but really what I mean is to maximize the absolute value of R11. Okay. Should put a plus or minus there. Okay, so I'll fix that. Okay, yeah. Yeah, because I really don't want to change how householder is done. Just to have positive diagonal entries. Okay, now. Okay, we'll go back. Okay. So then, now that I've taken care of the first column, now I move to the second column. And I'm going to define my notation here. bracket shows a more interesting example too, because we're giving a 4-column matrix, and most of the cases, there's no need to interchange a column. Yeah, I end up only doing one. So okay. I define A2 be A1 with the first row and column removed. Okay. And then what I'll do with that is A2 tilde A2 I2 and I2 pretty much kind of the same thing as this, except on a smaller matrix. Now, so it's called column 1 of A2, which corresponds to the second column of A, because we keep deleting rows and columns as we go. For column J, such that I look at column J of A2 tilde, it's a maximum length. In 2 norm. Okay, going from 1 up to n minus 1. Right. Now, one thing that's very important here is, here we computed the lengths of all the columns, and here we need the lengths of all of these columns. We do not simply recompute these. That would be wasteful. We don't have to. These we have to, but we can update these lengths to get these lengths. So what we have is A K2 2 norms squared would come from, so keep in mind, since column 1, 2, 3, 4, etc. of A2 tilde correspond to columns 1, 2, 3, 4 of the original A, all we have to do is take its 2 norms squared that we computed earlier. Oh yeah, these are vectors. Whoops, okay. And wait, K minus 1. No. K plus 1. Yeah. And subtract off the first element in row 1, column K plus 1, absolute value squared. So as we go from one column to another, the column lengths that we had, we just subtract off one element from the sum of squares. And this is true for K going from 1 up to n minus 1.
Excuse me, sir, I have a question.
Yeah.
Hold on. Step number 3.
Yeah.
When it's when we remove the first column, then we have a superscript 2, and then we have to do the by to swapping. So the A that we are removing that from was the updated A1 and not the original A1, right?
It's this A1.
So
So-
updated A1.
Yeah, we perform householder, we overwrite. Well, yes, so this matrix is one that had its first column already processed.
Okay, so it's after we have done everything. And we are removing, hold on, sorry. Okay, okay, I think I'm good. Yep, it's good. And just a dumb question, I think I know it, but E1 was the first column of identity, right?
Sorry, what?
E1 was the first column of identity?
Yes.
Okay, that's updated A1. Okay, thank you, that's all.
Now, one thing that's very important is, okay, here we compute the lengths of these columns, the original A. Oh, I should put a superscript of 1 here to take into account the swapping that happened earlier. Okay. So we update column lengths rather than recomputing them. Okay. Reason why update column lengths is a big deal, because this takes order n flops, the way I've written it. If you simply recomputed them, that'd be order n squared. You're doing this over n columns, order n cubed work to keep recomputing the column lengths. So that would be a significant part of the logarithm if we did that. Now, another very important point is here we're computing the lengths of the columns to figure out which one's the largest and then swap. But then we apply a householder reflection that affects all of these columns. And yet, this is still correct. And the reason why is this updating happened earlier, A1 being overwritten by the householder matrix times A1. Does not affects each column. Does not affect column lengths because you're multiplying each column vector in that matrix by an orthogonal matrix which doesn't change magnitude. Okay. All right, so and then we could just keep going. That A2 tilde is overwritten by a householder reflection. So that's H2 applied to the first column of A2 tilde is R2 to E1, where R22 is plus or minus the 2 norm of that first column. Yeah. Okay. Keep in mind, this E1 is 1 element shorter than this E1. Because we're working on a reduced size matrix. And then we keep going. We continue this process for all the other columns, like after A2 tilde is finished, we delete the first row and column of it. And so we're always working on the first column of our reduced matrix, which is the appropriate column coming from the original matrix. Okay, to stick with my notation I have in the notes. Okay, I make this tilde for H2. Just indicate it's working on a matrix of reduced size. So then A times the product of all the permutation matrices. Guess you only need, oh, wait a minute. You're only gonna, keep going up to column R, where R equals the rank of A. Because after that, there's not going to be anything more to do to reduce to upper triangular form. Okay. So what ends up happening is A I is equal to Q times a matrix of this form. Okay. So here we have the first R rows, and then here we have n minus R's rows of zeros down here. These are the first R columns, and then we have n minus R columns over here, and R is upper triangular and non-singular. I can put a tilde on this pi too, as well, to indicate working on a matrix of reduced size again. Okay, so to define all the entities we have here, Q is equal to H1, H2 up to HR. No tildes, where HJ is equal to identity of size J minus 1. And then we have HJ tilde down here. So it's a block diagonal matrix, just because HJ tilde is working on a matrix of reduced size. Okay. Pi is a product of all the permutation matrices. Because I've run out of room. I know, terrible board use. Pi 1, pi 2, up to pi r, where each one of these pi's is a full, let's see, n by n. They're n by n matrices, all of them. Because you're applying Then on the right of A, and A is M by N. And these permutation matrices are defined in terms of the pi tildes in the same way that the H's are defined in terms of the H tildes, where we have a block of identity in the upper left corner. There's a lot of notation flying around here. But in words, what's happening is make a largest column first by interchanging columns. Apply householder it to make it a multiple of E1. Then we toss out the first row and column, and we repeat that exact same process on the reduced matrix. So it really is identical once you trim it down like that. Because the rank of A is R, we only have to do this R times before we'll end up having all zeros down here. So then we can stop. Whereas before in the full rank case, we had rank A equal to N, so we had to apply N householder reflections.
As far as notation is concerned, anything that's not A1, A, or H1, pi or pi1 would have a tilde.
Pretty much, the only time I've deviated from that is when I first trim out the row or column, I don't have a tilde here because it hasn't been column swapped yet. But yeah, other than that, yeah, everything has a tilde. And everything except A1, H1, pi1 is of reduced size. So tilde or not, we can make that claim. Right, so the thing that we deal with now is, now that we have this decomposition, what do we do with it in terms of solving the least squares problem? And there's certain amount of choice here because the least square solution is not unique. So what we have is 2 norm of b minus ax squared. We're going to replace a with what we have is q, and then the modified r that we have, it has this block structure, and then pi transpose. So all of this is equal to a, because before I had a pi equals q times this monstrosity, I just multiplied this equation on the right, both sides, with pi transpose, because pi is an orthogonal matrix, because permutation matrix is orthogonal, times x. Now, I'm going to perform some decomposition here. So if I let Q transpose B have this decomposition, C and D. Okay. Where here we have a first R entries, and then this is M minus R. We also have pi transpose X. Broke down to U and V. So U is the first R entries, and then V is the other N minus R. What I can do to the expression inside this two norm is I can multiply everything in there by Q transpose on the left, because that doesn't change the two norm. So then I have Q transpose B, but that's C and D. Then I'll have R as 0, 0. And pi transpose X, that is Q and B. But the two norm of vector squared is the same as the two norm of the top part squared plus the two norm of the bottom part squared. So we end up with two norm of C minus the top part of this vector, which is RU plus SV. And then the bottom half, we're going to have 0 down here, so it's going to be two norm of D. Now, this we can't do anything about. That's Q transpose B, that comes from problem data. So all we can do is try to choose U and V so that this norm is 0. So there's different things we can do. What's called a basic solution is we just set V equals 0. And then we solve RU is equal to C. And R, for matrix R, capital R is little r by little r. And it's upper triangular, so we just use back substitution.
So is like D essentially going to be like our residual?
It is, yeah. So the magnitude of that is the residual norm.
Excuse me, sir?
Yeah.
What is it after RU equals C? And then R,
Okay, so the matrix R is R by R. So it's a square matrix where little r is a rank of A
mhm,
and upper triangular.
okay. R by R. And then back substitution.
Yeah. Yeah, so we're supposed to done all the QR column pivoting, then easy from there. Now, but this basic solution is not the same as a minimum norm solution. So the minimum norm solution that we would want the two norm of U squared plus the two norm of V squared is a minimum. But it's not so easy to do that. So this factorization that we have here is actually not the best way to go if you want the minimum norm solution. We need to try something else. But at least this decomposition that we have from QR column pivoting is a good starting point. We're just not done yet. That takes me to the next decomposition. Yikes. That is complete orthogonal decomposition. Okay. So our starting point is what we have from QR with column pivoting. So we have A is equal to Q RS 0, I transpose. Okay. So now if I just transpose everything, so A transpose would be equal to pi, then I have R transpose 0, S transpose 0, T transpose. Where R transpose is lower triangular. Okay. Now, so now what I'm going to do is apply additional householder transformations, or I just call them householders, to this matrix in the middle. And because this matrix R transpose is R by R, we have R columns here. It should be M minus R here. Okay. So I have R householder reflections to apply. To bring this to upper triangular form. Now I have zeros everywhere else. Basically, I'm getting rid of S. So now, so if I take this into account in here, my factorization of A transpose is updated to Z U 0, 0, 0 Q transpose, where Z is equal to the permutation matrix pi that we had earlier, and then these householders, but in the opposite order, which are written here. And Z is an orthogonal matrix because it's a product of orthogonal matrices. Now, a way to see this is, for this equation, I can move all of these p's to the other side. Remember, householders are their own inverses. So if I multiply both sides on the left, first by PR and PR minus 1 all the way down to P2, P1, then these are gone. And then I have P1 to PR in that order over here. So then I can replace this with P1, P2 up to PR times this in here. Yeah. And then that P1 to PR just fold into Z. Okay. All right, so now I can tell you what is the complete orthogonal decomposition. By transposing everything. So A is equal to Q times matrix L 0, 0, 0 Z transpose, where L is the transpose of U from before, so that is lower triangular. Also L is R by R, and it is non-singular. Now, A generally is not, well, generally it's not going to have an inverse. A may not even be square matrix. But if I do what I come as close as possible to inverting this, then I have the following. I'll call it A with a plus here, or you can take it as a dagger if you like, is Z, and then I have L inverse, because L has an inverse, 0, 0, Q transpose. That's called the pseudo inverse of A. Now, if A was square invertible, this would equal the actual inverse. So this is as close to the inverse as we can get. It's also known as the Moore-Penrose inverse. Now, the pseudo inverse has some properties that you would expect of an inverse. What we have is A pseudo inverse A is equal to A. So you can think of A and a pseudo inverse, or like one of the A's and pseudo inverse canceling out and leaving the other A. Similarly, a pseudo inverse, a pseudo inverse, a pseudo inverse. You also have a pseudo inverse times A is symmetric. if multiplied in either order. And normally we expect them to be identity. It may not be identity, or it's possible that one of them might be. But in every case, it's still symmetric. Actually, we'll see more of its properties in a little bit, although I may be running out of time. Oh, okay, still got some time.
Properties. They're set up. Typically how properties are set up when you have to show that it's true.
I think it is one of the problems I signed.
Of course.
Well, with the composition, it won't take long.
Yeah, those always turn out to be tricky because it's small little things. There's a lot of A's floating around.
All right. Oh, and in MATLAB, you can get the pseudo inverse by doing E inv of A as opposed to inv for a regular inverse. All right. So I don't know if I get through all of this, but I certainly want to show, because it relates to one of the problems I assigned, that this decomposition and this pseudo inverse is useful for getting the minimum norm solution of the least squares problem. Okay. So I can let fancy X be the set of all X in Rn that minimize the norm of B minus AX. It's, in this case, that the least square solution is not unique. Okay. So the claim I'm going to make is that if X belongs to X, so it's one of these least square solutions, and X itself is a minimum norm. Okay. Then X is equal to the pseudo inverse of A times B. So in the square and vertical case, we have X equals A inverse B. So now we have pseudo inverse B.
This is an interesting development.
What?
This is an interesting development.
Oh, yeah. A convenient one too. All right, so now I have to show this. All right. So I decompose Q into Q1, Q2, or these are first R columns. And then Z has similar decomposition, its columns. All right. Now, then we have the following. V1 transpose X is equal to L inverse Q1 transpose B. Now, I'm not going to show you why that's true because I've assigned that as a homework problem, but there are hints. I know. So then I'm going to pick up from here and carry out the rest of it. Okay. Now, so I go back here. to my complete orthogonal decomposition and take into account how I've just partitioned columns of Q and Z. So here I have Q1, Q2. You know what? I totally should not have erased the pseudo inverse. Whoops, okay. Right, so if I carry out all this multiplication of all these blocks, because I have all these zeros here, I have a simple representation of A. It's just Q1 L Z1 transpose. And if you take the formula that I just erased for the pseudo inverse and represent Q and Z in terms of Q1, Q2, Z1, Z2, you get a similar formula for the pseudo inverse. That would be Z1 L inverse Q1 transpose. Now, I can write X. Okay. So X is meant to be my minimum norm solution. So I could break it down into Z1 transpose times X plus Z1 Z2 transpose times X. Because you can show separately Z1 transpose plus Z2 transpose is identity. That comes from DZ transpose is identity. So these are orthogonal projections into complementary subspaces. Okay. Now, what I've written over here that you get to show in the homework, Z1 transpose X, I fill in the formula for it over there, and I get L1 inverse, Q1 transpose B. Oops, that should be Z2 transpose. I've written it Z1 earlier. But this right here is the pseudo inverse times B. Now what I'm going to do is I'm going to take the inner product of X with itself to get to 2 norms squared. So the 2 norm of X squared, which is X transpose X. So now I can take an expression on the right and take all right. Well, actually, it's easier to do it using a previous representation. Z1 transpose X plus Z2 transpose X. Transpose times same thing. Okay. Now, if I carry all this out, it's going to be a big old mess. I'm going to get X transpose, Z1 transpose, Z1 transpose, X. So I'm foiling this out, plus X transpose, one transpose Z1. Nope. Z1, Z1 transpose Z2. Z2 transpose X. Okay, and then I'm actually going to end up with, oh, okay. X transpose Z2, Z2 transpose V1, V1 transpose X. Finally, X transpose V2, Z2 transpose Z2, 2 transpose X. Ah. Now, Z1 and Z2 consist of columns from an orthogonal matrix. So they span subspaces that are orthogonal to each other. So Z1 transpose Z2 is 0 over here. Z2 transpose Z1 is 0. So the middle two terms are gone. What's left in the other two terms are the inner product of some vector with itself. So it's 2 norm of that vector squared. So it's just going to be 2 norm of Z1 transpose X squared plus Z2 transpose X squared. But the first term, Z1 transpose X, that turned out to be pseudo inverse times B. But because norms are always non-negative, that tells me that the 2 norm of A pseudo inverse B has to be less than or equal to the 2 norm of X. So there's no least squares solution with smaller norm. The only possibility left is that what if there's still what is equality still possible? Like, so what if there's a tie? But okay. Then when you take into account the fact that okay. But only A pseudo inverse B solves this equation. D transpose X is equal to L1 inverse Q1 transpose B and then 0. So another way of putting it, this vector has no component in the null space of A. It belongs to the span of C1. So because it's restricted to that subspace, because remember what I said earlier, if you have any least square solution, you can always add a vector from a null space onto it and have another solution. This has no null space component. So that's how we know that it's the only solution. So if X is distinct from it, this would actually be strictly less than. Questions about all this? Pull up a loop. All right, I have a few minutes. There's a few more facts that, while not part of the homework for this section, are still noteworthy. Thanks. If I let P equal a pseudo inverse, and I have to take a formula for a and a pseudo inverse using the complete orthogonal decomposition, it turns out to be Q, and then I have identity 0, 0, 0, Q transpose, where this identity is R by R. And you can show that P is symmetric and P is equal to its own square. So when that happens, say that P is called a projection matrix. The idea is you multiply by a vector by a projection matrix, it gives you best approximation of that vector within the range of P. Now, what's it projecting onto? So P is the orthogonal projection into the range of A. Okay. Now, so if I go back to the least squares problem for AX equals B, let B equal PB plus identity minus PB. So I'll call this B1 and this is B2. Then it turns out that if I take my least square solution, A pseudo inverse B, and multiply by A, then A times X is equal to B1. So B1 is in the range of A. Remember from a while ago, you not remember, AX equals B has a solution that exists if and only if B is in the range of A. So for least squares, generally AX cannot equal B. But if X is the least square solution, it does equal B1. A trimer is indicating it is 215. So, okay. So another way of putting it is, if B minus AX, the norm, is minimum, that means that AX is exactly equal to EP. Last thing, the residual R is equal to B minus AX. So I fill in what X is. So AX is equal to PB. So identity minus P times B. But that's B2. That's the rest of B. So another way of putting it is P projects onto a certain subspace, range of A in this case. Identity minus P projects onto the orthogonal complement of that subspace. So the residual is equal to the projection of B onto the orthogonal complement of the range of A, indicated by the perp symbol, which happens to be equal to the null space of the transpose. All right. That's the end of the notes. That's all for rank deficient least squares. Apparently I got another thing to fix the book, dang it. It never ends. And then we'll see you all on next Tuesday, it's my break. So then on Thursday, well, the main claim to fame of my advisor, the singular value decomposition that he developed first general purpose algorithm for is coming next.
So
Good
I have
luck.
a question.
Yeah.
I can stay after you stop recording.
Okay.